Hello, JerryTerry here with a little guest video where we'll be taking a look at Tynk's collision code. So Harlow recently rebuilt a bunch of Tynk's systems from the ground up to be better than ever, and in the process she hit me up with a pretty simple request. Dear Jerry, make me a script that handles all possible collisions that could ever happen. I do not want to have to think about whether one thing is touching another thing ever again. Please, though I might be paraphrasing a bit from memory. So here are the requirements. It needs to check collision for any sized object at any given angle or distance. This could be as simple as Tynk taking a single step or firing one of these guys from one end of the map to the other. It needs to check for both tile-based and object-based collisions. And it needs to operate entirely within this single script, using the information that's already given to it and output a specific set of info, which is a good place to start. When the collision script is called, it's done in this way. This is from Tynk's movement script. Whenever the player moves Tynk, this section of code is executed. So we feed it rules, which is a struct containing a bunch of useful info, the horizontal and vertical speed, which is actually the distance we want to move in pixels, and our starting X and Y position. So where we are now, where we want to be, and this struct, which contains the origin of the object, the dimensions of the object's collision box, for example, Tynk's looks like this, a list of objects to check for collisions against, and what tile map to use for the tile collisions. It also then quickly calculates the relative coordinates for the edges of the collision box to make things easier later. Tynk's rules look like this. Note that his list of collision objects consists of a single one, P entity, which is actually the parent object for all solid objects. So when it comes to checking, it'll actually be automatically checking for this object and anything that has this as its parent, which is handy. So that's it for the input. Here's what the script needs to send back out. We'll be returning whether or not it collided in the X or Y directions, what object it collided with, if any, and our new coordinates. If we didn't collide with anything, then it'll just be our starting position plus our distance, otherwise it'll be a new position lining up with whatever we hit. Note that our distance scales with this variable here, global.spritescale. This is actually because the game changes its internal resolution at certain points. For example, the dungeon in the demo actually has double the resolution of the rest of the overworld to account for its more detailed art style. Luckily, this can be accounted for by just multiplying the final outputs and the tile size. Okay, so with all of this in mind, it's time to write a script. Harlow gave me free rein here with however I wanted to approach this, and I'm gonna be honest with you here, I was pretty out of my depth. I've helped Harlow with little bits of code here and there, bug hunting and whatnot, but this was definitely my first project of this type and scale, and that's probably reflected in my code. But if any one of you armchair programmers pauses the video to be like, I don't know, so many arguments, why didn't you pack them into a struct? Or there's a much easier way to do this? Or why didn't you calculate the diagonal collision with this industry standard trick instead of throwing yourself into trigonometry hell? We will send Tynk to your house. And, well, she won't do anything specific, but do you really want Tynk in your house? So I decided to approach this in quite a segmented way. The function itself, SCR collision, will act as a master function that makes the essential starting calculations and then passes them off to a given subfunction based on the complexity of the movement. My plan here is to have the script always do the bare minimum amount of work needed per frame to be as efficient as possible. So here's what we do in the master function. First, we scale the tile size with our resolution multiplier as mentioned earlier. Then we shift our coordinates to the outer edges. These are the X and Y of the edge that would be the first part to ever touch another object. This makes both checking for collisions and lining up afterwards easier. Next, we find which grid squares we start and end in. This is just as simple as rounding to the nearest multiple of our tile size. Here I made this grid round function which rounds up or down to the nearest grid square for us based on direction. Then we figure out how many tiles our movement spans, which is essential for deciding how complex we need the check to be. Finally, we get those edge coordinates from rules and repack them into a list like this. This just makes it easier to pick a side based on direction. For example, say we either need the left or right side dependent on whether we're moving right or left. You can use this single line to quickly grab the correct one based on whether our direction is positive or negative. It's just handy. Alright, so now we split off into our subfunctions depending on the movement. If we're not moving at all, obviously we send it back. I actually did this right at the start, of course, so we don't do a bunch of unnecessary calculations for nothing. If we don't move outside of a tile, which will be the majority of Tynk's movement for example, then we don't need to do any tile-based checks. We do still need to check for objects though, and I'll cover that later. If we do cross between tiles but we're only moving in a cardinal direction, this is the simplest tile collision to check. Remember that this master function is executed per frame, so the odds of Tynk himself moving this far in a single frame are literally zero, but it's easy to illustrate this way. And the whole point of the script is to account for any possibility. Who knows what crazy teleporting moves Tynk might get. Anyway, for this, we simply check each edge between us and our destination. Note that we need to check a number of vertical tiles relative to our height too. If we hit anything, we propose that our new position should line up with the offending tile. I say propose because we're not quite out of the woods yet. We still need to check for objects. So we feed our starting and proposed ending positions into another little helper function, entity collision cardinal. This is basically the same principle but with objects. Capture our whole movement in a rectangle, list every object inside of that rectangle, then loop through the list and find the closest, which is what we've hit. Simple. Okay, so we've handled all cardinal movement, but what about diagonal? So our first and easiest diagonal case is crossing exactly one X and Y tile. For Tynk specifically, this is probably the rarest case, but it can happen. This one works in a similar way to the last one, but first we check the outer horizontal and vertical tiles to make sure there's enough room to get into the diagonal tile. This raises a situation though. Depending on our starting position, our back corners may or may not cross an extra tile. For this, we just quickly check if the line between our starting back corner and ending back corner intersects with the tile directly above it, and if so, we check that extra tile. Now you'd think that checking if one line intersects another would be so simple and common enough to have a built-in function. But it's not, so it's time to get mathematical. So we take this formula for calculating the intersection of two lines, arrange it into code, and there we go. You give it coordinates for the start and end points of two different lines, and if both intersection values are between 0 and 1, then the lines intersect. Simple. If all of these outer tiles are fine, then we check the diagonal tile. If that's empty, we move inside. Otherwise, we find which side of the tile we hit first and move there. Okay, so this is by far the most complex and unnecessary section of the script. What if we need to move diagonally across several tiles in a single frame? It's very unlikely to ever be needed, but hey, it's future-proof. Turns out that checking this kind of diagonal collision path along grid squares actually falls more into the domain of raycasting. So the idea here is simple enough. Follow along a line, and at every point where we intersect into a new tile, check for a collision along our width and height. Initially, I was checking all X intersections, getting the Y position via the hypotenuse, and then vice versa for the Y intersections. But this led to an obvious problem: order. So to correctly find what we hit first, after a bunch of looking into raycasting techniques, supercover line algorithms, etc., I found this one method of DDA raycasting where we follow along the line in real time. Here we track two different values for X and Y hypotenuse length, keep adding to one until it intersects, and then swap, and so on. Honestly, properly explaining this could take a whole video on its own, so I'd highly recommend checking out this video, which really helped solve a lot of my problems. It doesn't account for the ray having width, but it's a really good starting point and explanation of the trigonometry at work here. This leaves the final check, diagonal object collision. This is a bit easier actually. Here we have an object we want to move diagonally. First we take the rectangle of our intended movement, just like the cardinal version, and find every object within. But now we want to find the relevant corners of each object. See, whether or not we're colliding and what side we collide with can all be found by checking the position of the two closest corners relative to these three lines. If any of these corners are between these two outer lines, or straddle either side of them, we know that we have an intersection. And the position of this opposite corner relative to the middle line shows which side the intersection is on. Here, for example, if this bottom left corner is anywhere to the left of this line, we know we've hit the bottom. Otherwise, we've hit the left side. Obviously, it's impossible to hit either of the other sides. Now, you'd think that calculating which side of a line a point is on would be simple and common enough to have a built-in function. No, I had to do it myself, obviously. Here's a few helper functions I put together to find which side of a line a point is on, or by extension, whether any points in an array lie between two lines. Okay, so all that's left here is to group which objects collide on the X and Y side, find the closest of each by just finding the smallest difference in X or Y coordinate, and then checking whether this X intersect or Y intersect is closer. There you have our collision, and you can move along the hypotenuse until you hit it. So all we need to do now is shift our origin back from the outer edge to its original point, and we can return our values. Tynk is free to bump and smash into stuff as much as her heart's content.